ESD. ESD. People that's on microphone, then you know that the very inside. And you know the reading still. People need to keep myself. We just long I never microphone. Yeah. I think it's you do the scan of
Okay, so I think there are a lot many students on the MS team. So could you help me see my slides here because I already started recording. Anyone could help me to check? What do you can see? Hello? Anyone can check? Hello?
Yeah.
Okay. So it's moving, right? The slides? Okay, good. So first, let me announce something. So first, as I already told you about quiz tool, so for those of you who would like me to go through your quiz paper, so you have to email me, okay? So that we can make our individual consultation session this Friday afternoon, okay? So then the second announcement is this will be our last class on quantum physics. Okay, I have to cover about 4 or 5 chapters here. Maybe question just the 4 chapters. Next week is the final one. So what I will give you in the next week's lecture is an overview, final reversion. So that I will go through all the concepts which I think are quite important. So give you several questions on, so show you some past examination papers on optics, magnetics, and quantum physics. Okay, so next week is quantum, or it's a lot for quantum physics. It's just for final reversion. I think there are 6 additional questions, okay, put up, about quantum physics, was put up online in our course site. So that one, maybe I will just, randomly pick up some of them to talk about, because I don't think that is very important for the final examination. So that, but the solution, as I said, the solution will be provided. The solution will be provided. I will upload it online, both on our course site and through our MS Team group. So for the 6 additional questions on quantum physics, I will upload my solution there, because I think all the summary as well as past examination paper and tutorial question I covered here is already enough for you to solve. Is already enough for you to solve that additional 6 questions. So that next week I want to help you more, especially on the final examinations. So it will be an overview of the whole class, okay, not just example quantum physics. But the 6 additional questions, solution will be provided. Maybe after the final reversion, if we still have some time, maybe I will randomly pick up some of them, which I think are some difficult questions that I will go through, okay? But it's very important for you. As I said, that may not, as compared with the final reversion, the example I give there, so it's less important, but it does not necessarily mean it's not important at all. You should still look at that 6, tutorial question, try to solve them. Solution will be provided. Okay? Any question? Then the final thing is about the assignments. So that for those of you who have already finished the assignment and would like to submit in hard copy, you have to do today. Okay, submit to me after in or after your tutorial class. So otherwise, if you want to submit, follow the deadline. So April, midnight, 8th of April, you have to submit online through our course site. Okay, there is an assignment task created there. You can scan your copy and then combine it to a single PDF file and then submit. Okay. You cannot just scan page to page and submit one by one, so the system will not allow. You have to scan it as a whole, combine it to a single PDF file, and then submit. So if you want to do hard copy, you can submit it to me today. So of course, it's also okay if you want to submit the hard copy to me after today. But in this case, you can only go to my office. Okay? Any question? Any question? So if no questions, so I will start our class. So as I said today is the last lecture about quantum physics. So that I have to go very quickly because we have about 4 chapters to cover. So the first important concept we have to understand is what I call here the Schrödinger's equation. Okay, the Schrödinger's equation. Actually, the Schrödinger's equation I have already talked about last week, so that here I will just help you to go through, some most important concept. Schrödinger's equation is actually used to describe the wave function phi. Okay, wave function phi. So the second derivative of phi times a constant here plus u times the wave function equal to the total energy times the wave function. Okay, so this is the Schrödinger's equation. Then the meaning of the wave function is its absolute value squared, just describe the probability of finding a non-particle, at a certain position. So for example, if we use the Schrödinger's equation to describe the electron, and then this phi squared just describes the probability of finding this electron at a certain position of the space. If you want to find, for example, the electron within a certain region, A and B, you have to do integration of the wave function square from A to B. So that we have 2 examples to illustrate this point. Okay, so from our last tutorial. So if you still feel unclear, so go through our last tutorial example. So that if you still have questions, just let me know. We can have individual consultation. But what I have not told you about this one is the Schrödinger's equation. Last week we just talked about the probability function. We talked about a little about the Schrödinger's equation. Okay, so this is what I'm going to talk about in detail about how the Schrödinger's equation may test in the final examination. So if you take a closer look at the Schrödinger's equation, okay, so actually you find there are 3 functions in it. So one is a wave function phi, the other is the potential distribution. Okay, so that is how the potential is distributed. Okay, and the other is total energy. So which means the Schrödinger's equation relates the 3 parameter wave function, potential U, and total energy E together. So long how the final examination will test is okay. It will give you either 2 out of the 3 parameters, phi, U, and E, ask you to calculate the third one. This is the only way the Schrödinger's equation will be tested. Okay, as I said, 3 parameters in our Schrödinger's equation. Of course, this will be provided in your formula sheet. Okay, it will be provided in your formula sheet. What we will ask you to do is give you either 2 parameters out of the 3, U, this phi wave function, U, potential, and then the total energy. Give you either 2 out of these 3, ask you to calculate the third one. So I have some examples to illustrate, this testing point. So that what we have also to bear in mind is if we have free electron. Okay, if the question talk about something about free electron. So free electron is something that was not confined by any potential. So U is equal to 0. So that if for free electrons, we only end up with phi and E. So the relationship is only phi and E. So that normally people find that for free electron, its wave function always take this form. E times an exponential function. Then if you inject this wave function back into the Schrödinger's equation. Remember, okay, for free electron, U goes to 0. You will be able to find that this constant K, which is a wave number, okay, is related to the energy in this way. So K equal to 2 pi divided by lambda. This is what we call the wave number. This formula will be provided. But remember, okay, this K equal to 2 pi divided by lambda is given in the electromagnetics type, not in quantum physics type. Because this K, the wave number, is the same as the wave number of electromagnetic wave. So K equal to 2 pi divided by lambda. While our lambda here is what we call the de Broglie wavelength. Okay, the corresponding wavelength of the electron. Because the electron has dual property of particle and the wave. And this lambda is a de Broglie wavelength. Okay, K equal to 2 pi divided by lambda, similar as electromagnetic wave. But K equal to square root 2m divided by h bar, this will not be given. Okay, so I will suggest you remember this formula. Okay, K equal to square root 2m divided by h bar, this will not be given. Why it will not be given? Because you can inject this wave function back into the Schrödinger's equation to find out this relation. But of course, in that case, you have to do second derivative of phi. Right? When you do second derivative of phi, and then it will be minus k squared times phi, so that you have this h bar squared times k squared divided by 2m equal to e, so that it will be able to recover this formula. Okay, when you inject this guy back into the Schrödinger's equation, you will be able to get the last formula. But I would suggest every one of you remember this one. So the first part here will be given, but the square root of 2m divided by h will not be provided. Okay, will not be provided. I hope every one of you can try to remember this one. Okay, so these are all the concepts about the Schrödinger's equation. 3. So what are the probability function? Okay, so do integration to find the probability of the particle exists in a certain regime. Then Schrödinger's equation relationship between phi, u, and e. Finally, free electron wave function. Okay, free electron wave function. So here I have about 3 examples to help you look at how Schrödinger's equation may test in the final examination. Of course, the first one is our tutorial question. So it says, okay, in our space with 0 total energy, okay, with 0 total energy, then the wave function is given by this equation. Okay, wave function phi is given by this equation. Here A and L, of course, are constant. Then I want you to find out the potential energy U. Okay, as I said, how the Schrödinger function will normally be tested is give either phi, u, and e 2 parameters out of this 3 to find out the 0 one. So for this question, what 2 parameters are given? What 2 parameters are given? Yes, very good. Total energy is given. Phi is given. Find U. Clearly, this is okay. Once you say the total energy and the phi is given, you must remember, okay, this want you to apply Schrödinger's equation. Okay, these are some keywords. 0 total energy, which means this guy E is 0. So that in the Schrödinger's equation, we only have this guy and this guy. Phi is given, we will be able to find out U. Okay, phi is given, we will be able to find out U. So how to do this? As I said, when E goes to 0, we can put this guy the left-hand side. So we can put U on the right-hand side of the equation, cancel out a minus guy. We can get the second derivative of phi just equal to 2m divided by h bar squared U times phi. So as I said, phi is given. As long as we can get the second derivative of the wave function, we will be easily solve U. So this is how we do that. So here are some mathematical details that I don't want to go through it very much, because the first derivative and the second derivative can be calculated very easily. So the first derivative of phi is calculated in this way. And then you do the derivative of this function again, then you will end up with an expression this way. So you can quickly show the second derivative of phi is just equal to minus 2 divided by L squared times another function of x, then times the original wave function phi. Then you just substitute this phi back into this equation. Cancel out phi, you will be able to find that my U just given by this equation. Okay, U just given by this equation. So just some mathematics. Okay, Any question here? Good. So as I said, some conclusion. So you know, in my tutorial, sometimes I will give you some conclusion. Okay. So that is normally summarize how this part will be tested. So all the slides deal with a conclusion, which means is very important. You have to remember. Okay. So as I said, important thing highlight 3 times. How should your equation will be tested? Normally it will just ask you. The question will just give you 2 parameters out of 5 u and e. Then ask you to find out the third one. So if in the final examination I give you the wave function and the potential, then I ask you to find out the e. You should also understand how to do that. Okay. Again, I give you 5 and u. So normally 5 will be given. 5 normally will be the wave function will be given. Normally, if I give you 5 and u, and then you will be able to know how to find the e. Or I give you 5 and e, you will be able to know how to find the u. So just as our first tutorial question. Okay? Any question here? Any question here? Any question? Okay, no. Now let's look at the third one. Okay, so this is an additional question. I think tested out. Actually, the past examination were tested out many years ago. So just here, I want to show you. Okay, this one tests the wave function for free electrons. Okay, so here we have a free electrons with a wave function given by this equation. I want you to find out one the corresponding de Broglie wavelength, momentum and the kinetic energy. Okay, momentum and the kinetic energy. So what you should do that? First, you must understand when a wave function is given in this way, k, according to the formula provided in the electromagnetic part, wave number always equal to 2 pi divided by lambda. But now this lambda is all de Broglie wavelength. Okay, is all de Broglie wavelength. Then 2 pi divided by lambda equal to this k. So something in front of this guy 5 times 10 to the 10th power is k. Okay, so that k equal to this one, so that I can quickly get my de Broglie wavelength is about 0.126 in nanometer. Once the de Broglie wavelength is given, how can we calculate the momentum? How to get the momentum from the de Broglie wavelength? So then you need to refer to your formula sheet for the quantum physics part. De Broglie wavelength lambda always equal to h divided by the momentum p. Okay, h divided by the momentum p equal to the de Broglie wavelength. So that I might write p equal to h divided by lambda. Once lambda is given, okay, lambda is given, h divided by lambda is always a momentum. Okay, now we get the momentum. Okay, we get the momentum. h divided by lambda equal to the momentum. When we get the momentum, how can we get the total energy? Momentum P equal to mv, kinetic energy E equal to half mv squared. So that is P squared divided by me, 2me. Okay, so this is the kinetic energy, P squared divided by 2me, which is this is equal to half mv squared, So that when you do the calculation and then P squared divided by 2 times m, and then I divided by another 1.6 times 10 to the minus 19. Why I want to do this? Because the question wants us to express the kinetic energy in the EV. Okay, so that if you do not derive it by 1.6 times 10 to the minus 19, this is the kinetic energy in joule. If you want to exchange joule, change the energy from Joule to EV, you have to divide it by this unitary charge. Okay, unitary charge. Then we get about 95.6 EV. So you can see for the quantum physics, although some concepts are complex, but as I said, normally as long as you identify the right concept, the right formula to apply, normally a single formula will lead you to the final answer. Right? The first one is a relationship between k and lambda, right? Wave number and the de Broglie wavelength. When you apply this formula, you quickly get a lambda. The last one is the momentum of the electron. What's the relation between the momentum of the electron and the de Broglie wavelength? Right? P equal to h divided by lambda, similar to photon. then you also directly get the answer. Moment is given p squared divided by 2m, so that is the kinetic energy. Okay, also can be calculated by just one formula. So that this is what I hope you to, or you should try your best to digest. Okay. Identify some keywords in the question. Refer to your formula sheet to find out the right formula. So normally for quantum physics, one or two formula can help you to get the final answer. Okay. So any question about this one? Any question about this one? So if not, then I will help you to take a look. This is a past examination paper tested last year, just 1 year ago. So I don't think the chance of this one to be tested is very high. But what I mean is this question is very difficult. I think less than 20% of the students get 4 marks for this one. Okay, so now I want to show you the solution to this question. Just you know to show you. Although this question is very long, looks very complex, but as long as you try to acknowledge or try to understand the information given in the question, so it can be easily solved. Because I think for this question, some students, especially after the final examination, some of my students that said, okay, I think some concept is new. He never heard of this, in the lecture class, because this is said by by another professor, talking about teaching quantum physics. I think this question is a very good question. So although we have some new information here, but all the new information, all the new knowledge are already provided in the question. So that this is the case. Normally in the final examination, there are about 10 marks of the question are very difficult. But what I mean is why it's difficult, because there are some new information that is not taught in the lecture or tutorial class, but is given in the question. This is an example. Some student would like to say, okay, because we need as the university requires, normally for every class we need to set about 10 to 50 marks. That is a little bit more difficult. Not all the students can solve. But we should also consider difficulty that because if we said it's very difficult, no student can solve. That is not the purpose. So I think this question is difficult in a way, not because the math or the concept is difficult. It's because there are some new information given in the question. You have to understand and follow such new information. Okay. So now let's look at what are the new information given in the question. Okay. So firstly, it says that we have an electron. It was confined in a potential, and the potential distribution is when x smaller than 0, the corresponding potential is equal to 0. But at the position x larger than 0, its potential will now be u0. Okay, so it's a step function. The potential distribution is a step function. Okay, so of course, the potential can be any kind of function. Then the question tells us that in this case, the wave function always takes this form. Okay, 2 exponential function plus together when x smaller than 0. And then when x larger than 0, I will only have 1 exponential function. Okay, 1 exponential function. Then here, in this equation, it looks like there are 5 unknown parameters, A1, B1, A2, K1, K2. But then the question also tells us K1 and K2 are constant. They are only determined by the total energy E and the potential U. Okay, so in this case, K1 and K0 are already given. You just accept this. So students, when they say this, they don't understand why K1 and K2 in this way, and try to think about and derive that. And then they, of course, we can derive this. You substitute the Schrödinger's equation, this guy back into the Schrödinger's equation, and then together with U given here, you will be prove that K1 and K2 in this way. But this is not what the question wants. Some students, I say some of my students, when I talk to them after the final examination, I found this spend a lot of time. Try to prove K1 and K2 take this form, but this is you completely go to the wrong direction. The question here already give you what is K1 and K2. You just accept this. You don't need to understand why. You just accept that K1 and K2 is exactly taken this form. Then because here we have not, all these are the background information. We have not, asked you to do anything. So that, you just accept this is the wave function. And the corresponding K1 and K2 will take this form. Okay, as I said, A1, B1, A2 are all unknown constants. Then this question wants us to do is to ask you to find out the relationship between A1, B1, and A2. So for the first part, it shows you, okay, although here we have A1, B1, and A2, three undetermined coefficients, but it tells you that the wave function as well as its first derivative is continuous across the boundary x equal to 0. This is the most important information. Okay, this is the most important information. Since Newton, he just ignore this information and then don't know how to start this part. But this is the most important new information the question tries to deliver. So which means the wave function and its first derivative on both sides must be continuous. So which means, what does this mean? So you can say this wave function is only, so this solution, okay, of the wave function is for x smaller than 0. This solution of the wave function is for x larger than 0. The question tells us both solutions must be continuous at x equal to 0. What does that mean? Which means you submit x equal to 0 into the first expression and x equal to 0 in the second equation. The two values must be equal to each other. This is what continuous means. Okay, if you substitute x equal to 0 in the first equation, it's not equal to x equal to 0 in the second equation, then the wave function cannot be continuous because you will get a discrete, you will get a break. Only when the two values are the same, they are continuous. Okay, so this is the important new information the question tries to deliver. Okay, try to deliver. Then it says also the first derivative must be continuous like this, which means you take the first derivative of the wave function. So the left hand x smaller than 0 and x larger than 0, you will get two different first derivatives. Then you substitute x equal to 0 in the two first derivatives. They should also be the same. Okay, they should also be the same. So once you do that, you will be able to express, you should be able to express B1 and A2 in terms of A1. So this is, the most important part. This part takes 12 marks. Okay, you can say, because here are some new information given. Then continue. The question still try to give you some new information. Says once you get A1 and A2, then you will be able to define the so-called probability flux. The probability flux just taken, this form. For the incident side, it is related with A1 and K1. And the transmission side is related to A2 and K2. Still, as I said, these are some new information. You just accept this information. And then it wants you to find out what is the ratio between. So the transmission or transmittance is just defined as JT divided by JI, and then want you to find out the value of this JT divided by JI for E equal to 1.1 U0, and E is much larger than U0. This is the second part. Okay. So the last part want us to so this is for the transmission. The part C wants us to find out the reflection. So reflection will be easy, okay? Reflection is always equal to 1 minus the transmission. 1 minus the transmission. And the final part is want you to comment what's the difference between the quantum and the classical physics, okay? So if you encounter, for example, ask that, so what will be difference of the results we obtain here for quantum physics and the results we obtain for classical physics? So I want you to comment here, but just carries 4 marks. The most important thing here is still part A and part B. Okay, so let's look at how to do that. So now I explain what this question wants us to do, and also explain the meaning. So that, as I said, the question already gave us the expression for the wave function. Also tells you that the wave function as well as the first derivative is continuous across x to 0. So that, in order to make the wave function continuous, which means we have to substitute x equal to 0 in the first equation. and x equal to 0 in the second equation, let them equal to each other. So when you suppose x equal to 0 in the first equation, okay, k1 times x and will goes to 0, right? And then this e to the I will goes to 1. So that, for the first equation, it directly becomes a1 plus b1. The second equation, when x equal to 0, it goes to a2. Okay, it goes to a2. So that they have to equal to each other. So a1 plus b1 equal to 2. Okay, so this a2, this is the condition we get for the continuous of the wave function. Then its first derivative have also to be continuous. So that you take the first derivative of the first equation. Now it just becomes a1 times ik1, then times e to the ikx. The second part becomes b1 times minus ik1 times e to the minus ikx. Then if you substitute x equal to 0 into the equation, this e to the 0 goes to 0. So that it just becomes a1 times ik1 minus b1 times ik1. So this is for the first equation. The second equation just becomes a2 times ik2. Just becomes a2 times ik2. Cancel out I here. So this equation is obtained from the continuous of the first derivative. Okay. Then you cancel out I, you just get a1 k1 minus b1 k1 equal to a2 k2. Okay, two equations, just enough for you to solve, two unknown coefficients. Because this question wants us to express b1 and a2 as a function of a1. That means my a1 is lower. Okay, so that only b1 and a2 are unknown. Two equations just enough for you to solve a1. So that when you do that, what you found is, okay, my a2 is given by this equation. b1 is given by this one, okay? b1 is given by this one. So here I would like to especially highlight that when you solve the equation, what you found is, okay, a2 is just given by k1, a1, k2, a2. So if you just solve this part, I think you will be awarded about 8 marks out of the 12. Because what the question wants is express a2 as a function of a1, e, and u. So in this case, you have to, okay, remember, you have to substitute k1 and k2 from what is given in the question, okay, from these two parameters, okay? Only when you do this, okay, here, solve until here, you will be given 10 mark. Another b1, you will be given another 2 mark. In total 12. Okay, in total 12. If you only solve until here, you will be awarded 8 marks. Okay? Any question here? Any question? This is the most important thing. If this one you cannot solve, you cannot continue to the end. Right? But if this is given and then is obtained, and then the rest of the part are very easy. So if you have any question about here, just raise your hand. Any question? Any question? Sorry? Oh, you don't have to simplify. If you get to this, it's already very good. You don't have to simplify into here. This just show you in order to simplify the other step. If you obtain here or here, you will still be given the same mark. Okay, but you have to substitute k1 and k2 into the equation. Okay, you have to express k1 and k2 as a function of e and c. So otherwise, you cannot get 4 marks. Yes.
Okay, substitute.
K substitute, yeah, of course, because the question, the k here has a square root, right? The k here has the square root. It's proportional square root of e. You just substitute this k1 and k2 back into the equation, and then cancel out all the other. For example, this 2 pi divided by h. Okay, and then you will be able to get this one. Okay. Then I don't know. Then maybe there is some mistake when the lecture upload the formula in your tutorial. But this is what I get from the past examination paper. I know there are some problems in the tutorial because when he upload, he just forget about the formula. But in the final examination, if you go to the library, download the past examination paper. This formula are provided. This formula are provided. So otherwise it will be very difficult for you to solve. Otherwise it will be very difficult for you to solve. This formula are provided. You trust me. Okay. You trust me. Okay. The tutorial does not have is because of I think some misuploading, but I don't know. But anyway, these are the exact past examination paper. Okay. Okay. Any question? Any other question?
When they say continuous, you just equate they must equal each other.
Yes. Yes, that's right. Okay. So if no, then. Okay, from the first part, I already get the relationship between A2 and A1. And then for the second part, the question wants us to do is to find out JT divided by JI. This is what the question tells us is the transmittance. Okay, so that JI equal to this guy, J2 equal to this guy. You just substitute A2 by A1, what we get from the first equation. Then you will be able to show that my JT divided by JI can be, just be expressed as a function of E and U in this way. E and U in this way. Then for the first part, my E equal to 1.1 times U naught. If you substitute, that, back into K1 and K2, you will be able to find out, K1 and K2 are just given by, these two equations. Okay, these two equations. Okay, this is K1 and K2. Okay, and then you just substitute the corresponding K1 and K2 back into this equation. Or maybe here, you just substitute E equal to 1.1 times U naught. Okay? If you substitute E equal to 1.1 times U naught, and then both the bottom and the numerator and the denominator are a function of U naught squared. When you cancel out U naught squared, you will end up with this equation. So in this case, my JT is about 71%. My transmittance is about 71%. Then the next one is when U is much larger than U naught, what will happen? So you can say when U is much larger than U naught, which means my E minus U naught is approximately equal to E. In this case, you can say my K1 and K2 are approximately equal to each other, as well as my A1 and A2 are also approximately equal to each other. So in this case, my transmittance is about 1, is approximately equal to 1. Okay, so this is part B. So for part C, as I said, the reflection is just 1 minus the transmittance. So that for E equal to 1.1 times U, so I have 1 minus 71%, I get 29% transmission. So the other case, E much larger than U naught, the reflection is about 0. Okay, the reflection is about 0. Okay, any question? So as I said, transmission and the reflection always 1 minus T equal to the reflection. If the reflection is calculated, okay, 1 minus the reflection is the transmittance. Okay, so this is for C, very easy. So the last part you have to comment on here is normally for classical physics. As long as my kinetic energy is larger than, for example, the potential energy, right? This part can always cross. Cross the thread. So which means for classical physics, it tells that once my E is larger than U naught, then I will get total translation. If my E is smaller than U naught, I will get total reflection. This is classical physics. But this question tells us that, okay, this is not the case. Because for quantum physics, even my E is larger than U naught, I can get certain part transmitted, certain part reflected. Only when my kinetic energy E is much larger than U, I can reduce to the classical physics. Okay, total transmission, 0 reflection. Okay, so this is what we have to comment here. Any question? Any question? So as you can see, this I just highlight. Okay, some difficult question. What I mean is normally it will test you still the simple concept in our class, but maybe some new information will be provided in your, in that examination pattern. You should just try to digest and accept such new information. Combine it with what we learned in the class. Actually, you will be easily find out the solution to this question. I hope this one can give you as a good example. Then try to look at my solution. Digest all the information I give here. You can see that mathematics is very easy. You don't have to do all the integration or other complex measurement. mathematical manipulation. Only maybe the first derivative is already okay. But the most important thing is try to digest and understand the new information provided in the question. Okay. So if you say some part of the question has tell you some new information, so which means that will be the most difficult part of the final examination. Then a good example, a good strategy for you to solve, passing the written paper is when you find this question difficult. So for example, some new information is provided, I will suggest you to try to solve the other part. That's the most difficult question maybe you solve in the end. Okay. So yeah, this is the first part. Then the second part, as I said, yes. Any question? Okay, no. Then the second part is about quantum tunneling. Okay, so quantum tunneling, then I will just give you a brief or explanation about the concept. Okay, so first the concept is a lot what will be tested. Okay, but I think it's very important for you to understand something. So I will still talk about this. Okay, so first for quantum tunneling. Okay, quantum tunneling. So there is only one important formula is this guy. So what quantum tunneling is? So it says that if we have a potential barrier, you can view the potential barrier as a mountain or just like this wall. Okay, this wall has a certain height, and then when we insert, for example, an electron, onto this barrier, and then the electron will have certain probability to tunnel through this barrier. So this is what we call quantum tunneling. Quantum tunneling refers to the effect the electron or the small particle has a certain probability to tunnel through the barrier. Okay, and then the most important thing is what are the tunneling probability is given by this equation. So then let me explain what the quantum tunneling refers to. So for example, if here we have a wall or maybe a certain barrier, right? We want to jump through it. But if you cannot jump so high to cross this wall, so which means you will never be able to, to cross it, right? Cross it. Just like this is a ping pong ball. For example, if the ball has a certain height, if we cannot, through the ping pong ball go to the hole, it will always be dumped back by this wall, right? But the electron is different. If you throw the electron through the wall, even if it, even if it hits this wall, it may not be completely dumped back. It will have a certain probability to tunnel through the wall. Right? If you throw a ping pong ball, a very large particle on this wall, it will always be reflected back. You cannot let the ping pong ball to pass through the wall once it hit it, right? But if you throw the electron, if what you throw is the electron, it will have a certain probability to tunnel through it. This is what we call the quantum tunneling. Okay? What we call the quantum tunneling. So that we can say the tunneling probability is related first with the weight of this quantum barrier. Okay, L is the weight of the quantum barrier. Also, M of the electron, of course, is given. Also related with the potential height U and the kinetic energy of the electron. Okay, then there is one possible relation worth sigma. It asks you, okay, this formula will be provided. He said, okay, we have a quantum barrier in this form. I want to increase the tunneling probability of the electron. I want the electron to have higher probability to tunnel through the barrier. How many ways I can do that? How many ways I can increase the tunneling probability of the electron through the quantum barrier? Very good. What are the three? Very good. Increase E. Yes, very good. So you can say yes. That's right. Here we should have, three. How many ways for us to increase the tunneling probability? You should say we have the 3 ways. Because what we want is to increase E. Increase E, which means I want to increase, the product inside this bracket. This is a minus sign, which means I want to decrease this 4 pi L times this guy. If we want to decrease this guy, what we can do is either decrease the weight of the quantum barrier, make E smaller, L smaller. Or we can also make U, the barrier height, smaller, U smaller, or make my electron to be more energetic, increase U. So there are 3 ways. Okay. So as I said, just refers to the right formula and then find out the answer. So for our past examination, for our tutorial, we have this one. So that we have an electron kinetic energy given as 5 eV. The weight of the quantum barrier is 2. Yes, any question? The weight is 0.2 nanometer, so 2 angstroms. Barrier height is 5 eV. So I want you to comment what the probability that the electron will travel through the barrier, and B, what are the probability the electron will be reflected. Okay, I think this question is quite straightforward because both all L, U, and E are given, right? All L and E are given. You just refer to the formula for the traveling probability. Substitute the corresponding L, U, E into this equation. You will be able to solve the question. But some students make a mistake is because the question gives the energy in EV. When you substitute and do the calculation, because when you substitute EV into the equation, you have to change the energy from EV to Joule. Only in that case you will be able to get the right value. So this is why we have 2 elements. So this is the electron in kilogram, mass of the electron in kilogram, times 10 minus 5. This is in EV. We need to times another 1.6 times 10 to the minus 19 to change the unit from EV to Joule. Okay. In this case, you can get the right value. So do remember, if the question gives you the EV, when you use the energy in the EV to do the calculation, you need to times the unitary electron charge. Okay, unitary charge, that is 1.6 times 10 to the minus 19. Okay, so when you do this, you will be able to find out, the tunneling probability about 1%. Okay, so which means if you throw 100 electrons onto the wall, onto this barrier, and then 1 electron is get 99% will be reflected back. Okay, then the reflection, of course, as I said, reflection is 1 minus the transmittance. Okay, then it's about 99%. Okay, 0.9897, about 99%. Okay, any question? Good. If no question now, we have the I think this is for chapter 9, if I remember correctly. This is for chapter 9, quantum state of atom. Quantum state of atom, which means you have to. There are something you have to remember. There are a lot of difficult concepts here. So what do we mean by the quantum state of atom? So here I would like to remind you what is a hydrogen atom. Okay, hydrogen atom, which means that electron circulates this atom. Okay, 1 electron circulates this atom. It will have different energy level. Right? Different energy level. It will have different energy level. But that is only for 1 electron. If we have 2 or more electrons circulate the atom, the situation will be very difficult. Okay, for hydrogen atom, the energy of the electron circulating the atom is only given by the quantum number n, right? If you remember, the hydrogen atom is minus 13.6 eV divided by square. So that the total energy is only given by a single quantum number. So that for a hydrogen atom, when you only have 1 electron, a single quantum number n is already can help us to describe the probability of that atom, because we will be able to know what are the radius from the orbit to the from this electron to the nucleus, and what are the total energy. But if you have a lot of electrons, and the situation becomes very complex. You can no longer use just a single quantum number to describe its orbit and its energy. You have 3. You have to use 4 parameters. So the 4 parameters here, I don't think the question will ask you, about the physical meaning of all the 4 parameters. So here I will just quickly go through. So that the first parameter is the principal quantum parameter. So this is just this n is just similar to the quantum number in the hydrogen atom. It just describes the average distance from the electron to the nucleus. And we also have the Arrhenius quantum number n. So that describes the shape of the sun shell. Okay, the shape of the sun shell. Okay, that is the shape, because if we just have a single electron, the single electron is always doing the circular motion. But if we have more electron and then depending on L, the electron can either do this circular motion or do this bowling shaped motion. So that's the electron will have different orbits. We have different orbits. And the L just describes the shape of the orbit. So this number N and L are the most important number because quantum number, because it will just give us the energy of each orbit, the energy of that electron, the energy of that electron. But there will be different, each energy level, can occupy different, electrons, different electrons. So this is why you have to remember something. Okay, magnetic quantum number just describes the orientation of the orbit. For example, if we have this bowling shape, which means can respond to my L equal to 1. Can responding to L equal to 1, so which means my electron just do this, this H-shaped motion. Okay, so it has 3 orientations, and then the quantum number just M just describes the orientation of the orbits, and then the final one is the spin. Is the quantum number of the spin. It can only electron spin. It can only be positive 1 divided by 2 or negative 1 divided by 2. These are the 4 quantum numbers. Then, in chemistry, what the people do is okay. So it will just use number to describe the principal quantum number. Okay, as I said, the principal and the azimuth quantum number are the most important 2 parameters. Okay, so that it will just use this 1, 2, or 3 to describe the principal quantum numbers. And then it will use SPD to describe the azimuth quantum numbers. Okay, so this you have to understand. It will use SPD. Why SPD? Then I don't know. This is okay. The quantum physics already agree, internationally. They use SPD to describe L equal to 0, 1, and 2. L equal to 0, 1, and 2. Okay, 0. S equal to 0. S corresponding to L equal to 0, P corresponding to L equal to 1, D corresponding to L equal to 2. Okay, so that's, but the case is what you have to remember. The most important thing you have to remember is the following formula. Okay, so for example, 1s, which means n equal to 1, s equal to 0. For this 1s orbit, it can occupy 2 electrons. Then after 1s, then we have 2s. Okay, this is what you have to remember. I don't think it will be provided in your formula sheet. This is something you have to remember. So that's the electron from 1s, 2s, 2p, 3s, 3s, 3p. Okay, it will always follow this line. So what the quantum number of atom will be estimated? Okay, I give you the atomic number of a certain element. So which means, for example, hydrogen. It has 8 electrons. Then I want you to put the 8 electrons in this orbit. And then how should you put this 8 electrons? This is what it will be normally tested. So that some topic you have to understand is the electrons are always tend to occupy the lowest energy. So just like when you buy some house, you want to get the highest top. The electron want to go to the lowest energy because the highest the room is. Okay, and then you will from the view, or maybe it will be more quiet, and the view will be better. So this is why you want to get the higher level. Just because the electron tend to occupy the highest energy. So for example, if I have 2 electrons, then both electrons will go to 1s level. Then if 1s level already occupied, if I have 4 electrons, 2 at 1s level, 2 will at 2s level. And then if I have 6 electrons, the remaining 2 will go to the 2p level. Okay, will go to the 2p level. So this is what normally the electron will do. So yes, this is give you the possible value for each quantum numbers. For the principal quantum number n, so that is the orbit. It can be only possibly from n equal to 1, 2, and 3. So as you can see, n always start with 1, 2, and then 3. So as I said, for the final examination, you just remember until 3p is okay. Okay, 1s, 2p, or 2s, 2p, 3s, 3p. So just remember this. The first 5 orbits is okay. But what you have to understand is for the S level, maximum I can only get 2 electrons. P level maximum I can get 6 electrons. Okay. So that, as I said, we only test you until 3p is okay. So you just remember 1s is the lowest one, 40 is 2s, then 2p, 3s, and 3p. Okay. So just remember until this is okay, because we will never test you anything that is higher than 3p. Okay. So that yes, as I said, n can be only positive integers. Then L can only be a finite number from 0 to n minus 1. So for example, if my n equal to 1, my L can only equal to 0. So this is why at the n equal to 1 orbit, I only have s. At the n equal to 2 orbit, I can have s and p corresponding to L equal to 0 and L equal to 1. Okay. So at 3, n equal to 3, I can have L equal to 0, L equal to 1, and L equal to 2. So that can responding to, okay, this SPD. Okay, this SPD. But as I said, 3D will not be tested. So that remember until 2p is okay. Then the azimuth quantum number can be either minus 1, 0, and 1. So the electron spin minus 1 divided by 2 and positive 1 divided by 2. Okay. So then, as I said, if you want to find the azimuth quantum, if you want to find the how the electron will occupy different orbits, what you have to apply is two principles. The first principle I already told you. Okay, electron will always tend to occupy the lowest energy. So for example, I have 3 electrons in this lithium. Okay. So that 2 electrons will first occupy 1 s level, and then the other remaining electron will have 2 s level. And then if I have this, now if we have this volume, okay, so n equal to 5, so 2 in 1 s level, because each subshell orbit can only occupy 2 electrons. One spin up, one spin down. Okay, so which means one is positive 1 divided by 2, the other is negative 1 divided by 2. Okay, so that 2 in 1 s level, 2 in 2 s level, the other remaining one will be in 2p level. Then the most important thing is about for carbon. Now I have 2 electrons in the 2p level. So that when you are in the 2p level, because for the 2p level, it has 3 kind of orbits. You have because 3 different orientations corresponding to L equal to minus 1, 0, and L. Then the electron will always tend to occupy different orbit with the same spin. So that which means the 2 electrons will not just occupy the single room. They will tend to occupy different room with the same spin. So this corresponds to L equal to 0, L equal to minus 1, and then it with the same spin up. Okay, ms equal to positive 1 divided by 2. Positive 1 divided by 2. And then another electron come to, for example, for this nitrogen, okay? And then 3 of them will just occupy this 3, different orbit. And then if I have one more, and then I have no choice, I can only occupy it with, for example, with the other pair to form a pair, okay, spin down. So this is the way how the electron will occupy different orbits. So that in order to, so now you may find that there is a little bit confused. Then I will just explain this through, two examples. Okay. So first one is our tutorial question 3. So here I want you to write down the electronic configuration for hydrogen and then the corresponding quantum numbers for the eta electrons. Okay. Now, okay, may I have your attention, please? Now let's look at how can we do that. As I said, what you have to do is put your electrons into this 1s, 2s, 2p, 1s, 2s, and 2p. So you should make sure that the superscript plus together equal to 8, because that is the superscript just means how many electrons are in such subshell. So as I said, we start with 1s, 2s, and 2p. 1s level we have 2 electrons put there. Then the third and the fourth electrons will occupy 2s. Then the remaining 4 will be put in 2p because 2p can occupy in total 6 electrons. So that if we put, the 4 electrons in the 2p, then that's already okay. Then this is what we call the electron configuration. The electron configuration. Normally, this kind of question will worth about 6 marks. And then the electronic configuration will worth 2 marks. So that what you do is just put the 8 electron in this 1s, 2s, and 2p. Make sure that subscript summing up together equal to the atomic number 8. Okay? So this is the first thing. And then for each electron, you have to write down its 4 quantum numbers. So that worth another 4 marks. Yes? Okay? Then let's look at for the 2 electrons in 1s level. So 1s always means n equal to 1. S always equal to L equal to 0. Okay? S means L equal to 0 and ML also equal to 0. This is the meaning of S. Both L and ML equal to 0. And then because there are 2 electrons in 1s level, these 2 electrons has to be spin up and spin down. Because in an atom, no 2 electrons can have the same, exactly the same 4 quantum numbers. Okay, so you can say there's 3 quantum numbers are already the same. So the last, different quantum parameter will be their spin. Okay, so the 2 electrons in the 1s level will be 1 spin up, positive 1 over 2, negative 1 over 2. Then for the 2 electrons in the 2s level, as I said, this 2 always corresponds to n equal to 2. S always means both L and ML equal to 0. So for S means both L and ML equal to 0. Okay, and then corresponding MS again is positive 1 divided by 2 and minus 1 divided by 2. So now we have 4 electrons in the 2p level. So what we should do, as I said, for p level is all 2p, which means n equal to 2, L equal to 1. ML can be either minus 1, 0 or positive 1, because we have 4 electrons there. Okay, as I said, the first 3 electrons will tend to occupy different ML with a sense spin. Okay, so that you should put the first electron, in this n equal to 2, L equal to 1 orbit. Their MS should be all positive, while ML should range from minus 1, 0 to positive 1. So this is the idea, how you can maximize this ampere spin. Okay, the Higgs principle said, okay, what we should do is we want to have the maximum number of the electron have ampere spin. Ampere spin, this means they have they have the same N, L, and ML, but different MS. That is what we call paired spin. Ampere spin, which means their spin are the same, but ML are different. So that to get the maximum ampere spin, the first electron should have the same spin, but occupy different ML. So that the last electrons, okay, it should be a spin down electron, of course, but its ML can be either minus 1, 0, or positive 1. So that you don't have to write all the possible value for the last electron. You just write like 1 is okay. So which means this electron can be either ML equal to 0, ML equal to minus 1, or ML equal to 1. Both are all right. Okay. So this is what we do, for write down the quantum number. Okay. Any question? So if no question, we have a past examination paper test about, I think 5 years ago. So this is an additional question that I would like to talk about. So that for for atomic number carbon, so its atomic number is 6. I want you to list the electronic configuration and then write down the corresponding quantum number for each electrons. So as I said, we have this 1s, 2s, 2p, 6 electrons. Of course, it should be 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. Right? Any question here? Okay, if no question, we need to write down its quantum number. As I said, for 2 electrons in 1s, always n equal to 1, L and ML equal to 0, spin up, spin down. For the 2 electrons in the 2s level, always n equal to 2, ML equal to 0, spin up, spin down. So that for the 2p level, as I said, what I would suggest you to do, so you always first list the spin up. So although you first list the spin down is okay, but I would suggest you first list the spin up. Okay, because now we only have 2 electrons. These 2 electrons should be always 2 spin up. It can either occupy ML equal to -1, 0, 0, 1, or -1 and 1. Okay, so all the 3 here can be correct. You just need to write down one of them. You don't have to do all the 6 together. Okay, so if you want to first list the spin down is okay. Spin down is okay, but do remember, okay, my ML has to be different. Okay, so this is the way when you write down quantum number. Okay, any question? Any question? Okay, so if no question, then I have, so this is one of the difficult questions. Okay, so it tests you until 4s, so that this is why it gives you some additional information that 4s has energy level 3 smaller than 3d. So which means after 3p, you should put the 2 electrons in 4s level. So that it wants you to write down the corresponding electron configuration for calcite and the corresponding quantum number for the subshell. So of course, in this case, what we should do is put the 2 electrons in first 1s, 2s, 6 electrons in 2p, and then followed by 3s, 3p. The last 2 electrons in this 4s level. Okay. So that's how to write down the quantum number because of the limitation of time. So I provided the solution in my slides. You just compare your solution with mine here, okay? Because I already talked a lot about how to write down electron configuration, okay? You just take a look at the solution yourself. So then I will come to the last concept. I think this is chapter 10, okay? Chapter 10, not chapter 11, okay? About the X-ray generation. So the X-ray generation. So that to understand X-ray generation, you should compare it with the photoelectric effect. So let me remind you what the photoelectric effect is. So it says if we inject high energy photon or high frequency photon onto the metal, then it will be able, if the frequency of the photon is larger than the cutoff frequency, it can drive the electron out of the metal. Right, that is the photoelectric effect. Or in other words, in the photoelectric effect, we use a photon to generate the electron, right? Photon to generate the photocurrent, that means the photon to generate the electron. Then people ask the other way around. If we inject, for example, high energy electron onto a certain material, such as metal or some other crystal, will we be able to convert the energy of the electron to photon? Right, we can use photon to emit electron in the photoelectric effect. Can we do the other way around? We use electron to generate the photon. Okay, photoelectric effect, let me remind you, highlight again. Photoelectric effect is to use photon to generate the electron. And the X-ray generation is to use high energy electron to generate high energy photon. Okay, high energy photon. And then people found that yes, we can do that. Actually, this is the experiment people done in the past, which was also awarded the Nobel Prize. He just incident very high energy electron onto a material, bombarded, for example, certain kind of material, such as metal or some other things. And for the yes, in this case, we can generate a new kind of wave that is X-ray. That is X-ray. Then in their experiment, so first let me explain to you what we found in this experiment. Okay, in this experiment, if they found that okay, if the electrons are high enough, they will get the for example this material to emit in the X-ray spectrum. So X-ray its wavelength is several tens of picometer, but the emission spectrum is very interesting. Okay, so first it has a broadband. It has a broadband similar to the background, emission. This broadband background information. Apart from this broadband background information, it has also 2 peak emission wavelengths. What they call K alpha and K beta. K alpha and K beta. This is what people measure in their experiment. So of course, when you measure this in the experiment, we want to explain this spectrum. So that what people found that okay, this is because because what we inject is a bunch of the high energy electron, and then the broadband emission is when the electron incident directly interact with the atom. the atom will create a certain potential that will slow down the high energy electron. When the electron is slowed down, of course, its energy will be transmitted to photon to emit X-ray. So this is the property of this broadband emission. Okay, so this is the electron interact with the atom, for example, because of this Coulomb effect or Coulomb repulsion, something like that. So that is the transfer energy into into photons. So it's a very broadband one. But apart from this broadband one, we also have two discrete emission spectrum. What is that? Then what the scientists found is okay. Apart from the electron interacting with the atom, the electron may also collect with some electron in the inner core. In the inner core of the atom, so that it will remove, some intrinsic electron of this atom. For example, it remove the intrinsic electron of the atom at the n equal to 1 level. So that originally there is 1 electron, but because the electrons are so energetic, it can pass through all the other electrons in the outer core and then remove the most inner electron. Then because the most inner electron, this guy here has the lowest energy. Once it becomes unoccupied, the electron at the outer shell will transit to the inner core to emit a certain photon. Because the discrete emission is similar to the discharge of a certain kind of element, it will also emit at some discrete frequency. And the people found that okay, yes, these two wavelengths, okay, just matches with the energy difference between the L and the K level and the M and the K level. Okay, so that they found okay, maybe it's because the electron, just the output electron, just collect with 1 electron, collection with 1 electron at the most inner core, so that both the incident electron and the electron at the inner core become free. They are removed to to infinity, so that the electron at M and L will jump to the K level to emit a photon. So that people said the K alpha can respond to the transition of electron from L to K to emit a high energy X-ray. And then this K beta can respond to the electron transit from M to K, so it will emit another high energy, photons. Okay, so these are the two typical emission spectrum, in the X-ray. So now I already explained two important properties. What are the physical origin of this broadband emission, and then what are the origin of this two peak, generation? Then the final important property is okay, the cutoff frequency of this broadband emission. Okay, this cutoff frequency of the broadband emission, which means okay, all the energy of the incident electron are transmitted to photon. Okay, so in this case, my H times this maximum wave frequency, so which is H times Z divided by the cutoff wavelength, should exactly equal to the kinetic energy of the incident electron. Okay, so this is the meaning of the cutoff frequency. So that for X-ray here we have 3 important concepts. Okay, normally it will always be these 3 important concepts. The first is what are the origin of this broadband response? I highlighted for you here. This broadband continuous emission band is a result of the atom slowing down the electron, so that when the electron strikes the metal, it will emit this broadband on a continuous frequency. Okay, so the question may ask you to explain what are the broadband response, and then this, what I highlighted in the green box here is what you should comment here. Then it will also ask you what are the origin of these two characteristic emission wavelengths. You should say, okay, these two characteristic emission wavelengths result from the electron transit from L equal to K. This is K alpha. K beta can respond to the transition of the electron from M equal to K. Okay, these are the second important property. The last important one is how to calculate the cutoff frequency. Okay, Hc divided by lambda cutoff always equal to the kinetic energy of the incident electron. That is the cutoff. Okay, so X-ray generation only these three important concepts. Only these three important concepts. So in order to let me see. Okay, yes. Here I have two past examination papers. Okay, to for you to to understand the X-ray generation. So here first, the figure on the right shows the X-ray spectrum emitted when a 37 keV electron bombard the target. Then it shows you two sharp typical peak A and B, which belongs to the K band. I want you to explain again the physical region of this broadband background spectrum, and then what are the origin of these two peaks. Okay, then I want you to identify. I want you to identify which peak is K alpha, which peak is K beta. Okay, as I said, K alpha always happen at the longer wavelengths. K beta at shorter wavelengths. Okay, so B should be K alpha, A should be K beta. Then I want you to determine the cutoff frequency here. This emission is already given. So as I said, these are exactly Tesla about these three concepts. So what you should do here, okay? This broadband continuous background is because of the electron are slowing down or deaccelerate by the atom of the target. Okay, by the atom of the target. So that the energy of the electron are gradually translated to the energy of photon. Okay, energy of photon. This is part one. So that, as I said, K alpha should happen at a longer wavelengths, K beta happen at a smaller wavelengths. So that we should comment on here. A is K beta, B is K alpha. And the K alpha is caused by the transit of electron from L to K, while K beta from M to K. Okay, so this is for this part, all about explanations. Okay, so explanation from the broadband background emission, as well as the two typical emission wavelengths. Then the last one, I want you to calculate what are the cutoff frequency of the X-ray emission. So as I said, the cutoff frequency and the cutoff wavelength Hc divided by lambda c, Hc divided by this lambda cutoff frequency should equal to the kinetic energy of the electron. The kinetic energy of the electron is already given as 37 keV. So that lambda c just equal to Hc divided by Ek. So again, when we calculate the emission wavelength, we need to first change Ek from 37 keV to Joule. We have to times the unitary electron charge. Okay, so which is 1.6 × 10⁻19. So that I found my lambda c is about 33.4 picometer. 33.4 picometer. Any question here? Okay, so no question. Maybe I have one last examination paper. So okay, this is also an additional question I would like to talk about here. Test about 6 years ago. So here we have an electron deaccelerate from rest by an electron potential. Okay, so which means in the beginning I have an electron with zero kinetic energy, and then I accelerate this electron by a very large potential, and then let this a high energy electron after accelerated by the potential to bombard a metal. Okay, you see I use a high energy electron to bombard a metal. Which means I want to do X-ray generation. Okay, I want to do X-ray generation. Once you say the keyword, high energy electron bombard the metal or bombard a certain crystal, which means I'm doing X-ray generation. Then it will generate K alpha and K beta lines. Given that K, L, M, L, the energy level of the metal are 70, 11, and 2.3 keV. I want you to determine the minimum value of the accelerating potential that will permit the production of K alpha and K beta, and then the corresponding wavelengths of K alpha and K beta. Okay, K alpha and K beta. So that's the first part. Actually, is very interesting. Okay, I want to generate K alpha and K beta lines. This is the question. Okay, the electron. Their energy should not be the energy of the photon corresponding to K alpha and K beta, but it should be it should have an energy high enough to move the electron at the K level back. Because as I said, K alpha and K beta can respond to the electron transit from L to K or L to K. So first, my incident electron must be energetic enough to remove an electron at the K level. If the energetic electron have to remove electron at the K level, which means my incident electron should have an energy that will match the energy of K. That will match the energy of K. So which means in this case, I want the energy of my incident electron. Okay, the energy of the incident electron, is resulting from the acceleration by the potential. So Q times V is the potential energy of the potential. When I accelerate it by this potential, then it will be transmitted to EK. I want this EK equal to Q times V is equal to 70 keV. It should be at least 70 keV, so that you will have enough energy to remove the electron from this K energy level. The energy level of K is 70 keV as common by the question. Then I use 70 keV divided by the electron charge E. I get my V is about 70 keV. So 70,000 volts. The voltage has to be 70,000 volts, okay, which is very large in order for my electron, in order for my incident electron to remove the electron from the most inner core of the atom. So this is the first part. So that's the second part. It wants you to calculate the corresponding emitting wavelengths of K alpha and K beta. Okay. So of course, in this case, the emit photon from this K alpha level, so their energy Hc divided by the corresponding lambda should equal to the corresponding energy difference between the K and the L level. Okay, K and L level. So K level is 70, L level is 11, if I remember correctly. Okay, and then the corresponding difference, energy difference between L and K is about 59. And then this 59 keV should equal to Hc divided by lambda K alpha. So when you do that, you find that, okay, the wavelength for this K alpha is about 21 picometer. So we find that for K beta, the energy of the K beta 9 should equal to the energy difference between K and M. So which is 70 keV minus 2.3 keV. Okay, the Hc divided by this value will give us the wavelength for the K beta 9, so which is 18 picometer. Okay. Any question here? Any question? So this is how the X-ray generation will be tested. Okay. Then we have the last chapter, chapter 11, so about the laser and the laser light. So we have no tutorial question here. But here I would also like to highlight for you how this laser will be tested, because there is a possibility what you comment on. What are the three criteria to generate laser light? So the three criteria to generate laser light I already highlighted for you. So first we need to have a metal stable state to hold the excited electrons. Then we need a cavity to provide positive feedback. Okay, to provide positive feedback. Then finally we need the gain is larger than the loss. So which means more atom and the metal stable state than at the ground state to create a population immersion. Okay, so three keywords. One, we need to have a metal stable state. Second, we need to positive feedback, cavity to provide a positive feedback. Three, gain larger than loss to generate the population immersion. These are the three criteria to have the laser generation. Okay, laser light. So as I said, for the laser part, what it will be testing is what are the three criteria to generate laser. So here I highlight for you, we don't have any tutorial questions, okay? But the criteria to generate laser, okay, is also very important. You have to remember, okay? You have to remember this. If the question, for example, one of the questions asks you, what are the requirements for the laser? And you remember to comment on these three, okay? So yes, this will be the end of this class, also the end of quantum physics. Okay, as I said last week, I will give you an overview of the whole course from optics, electromagnetics to quantum physics. So that for preparation, I hope every one of you should try to take a look at my slides, all the summary slides, to prepare for the next week. Because the next week I have 1.5 hours to cover all the 12 chapters. So of course it will be quite intense. I hope everyone of you should try to do something related before attending the class. Okay, so if no question in the class can be dismissed. If you have any question, please come to me now.
Oh, can I extend?
Sorry? You want what?
So instead of 1.5 hours, you cannot do 2 hours.
Sorry?
Extend your time.
Yes, I can extend the time. So everyone is okay, right? But anyway, for any one of you, so actually I intended to have 2 hours. But because I want to also talk about some quantum physics, there are 6 additions. What I planned is the first 1.5 hours, 1.5 hours, I talk about all the reversion about all the optics, electromagnetic physics. And then I talk about some remaining additional factors of physics that will be about 2 hours. Okay, but anyway, if some of you next week want to leave earlier, it's also okay. Okay, because I will report. So as I said next week it will be about 2 hours final revision. Okay, but you can leave at 3 p.m. if you have some other class. Okay, so I will prepare that class for 2 hours. Yes, that's what we will do. Okay. So any question for the next class?
Next is what what's that? A alpha beta waveform.
Yes.
Further up here. Understand again. So understand for this one, right? We come from M to K.
Yes, M
from
to K.
higher energy state to lower energy
Yes.
state. Then for this one, we come from L.
L to K.
Yeah, but L is lower energy than M, right?
Yeah, lower is lower than M.
Okay, so when we come from M to K, more energy is emitted.
Yeah, more energy is emitted, so the wavelength is smaller, frequency is higher. Yes.
So how come like here more energy is emitted, but how come the intensity is lower?
Yes, this is a very good question. More energy is emitted, but you know, what we do here is we have a lot of electron to incident, so that actually a lot of atoms there, this part was removed. But whether whether it's L jumped to K or M jumped to K, okay? So that depends on the probability. So that the probability of L to K is higher than the probability of M to K. Why? Because L is closer to K. So which means more electron are jumped. For example, here we remove about, just give an example, 100 electrons from Km. Okay. But maybe 90% will be L to K. Only other 10% from M to K. So although the photon energy is higher, photon energy is higher, it just means the emitting wavelength is smaller.
Okay.
Yeah, but the total energy, okay, is the emitting energy times N. So although the photon energy is higher, but the number of generated photon is much smaller than K alpha 9, so that the intensity is still smaller.
Okay.
Yeah, this is because something related with the probability. Probability. But I don't think this will be tested.
Okay.
This will be tested. This will be tested because if you want to explain why this is higher, that is related with the photon lifetime. You just need to understand the probability of L to K is much higher than probability from M equal to K. So that its intensity is higher.
I see. Okay. Then how come there's a cut off here? Because I thought like whenever it shines, it should keep like it should like for example, if we keep shining a beam of electrons, it should keep the atom should keep absorbing the thing. How come suddenly here is like from here onwards it's like nothing happening?
It's the electron. The atom can either absorb, for example, 50% of the kinetic energy, or absorb the whole kinetic energy, so that the electron is free.
Okay.
Right. The whole kinetic, if the whole kinetic energy is absorbed by the atom can only emit this cutoff frequency, because it cannot emit. So the energy has to be conserved. The atom emit a photon, which is energy is even larger than the energy of the electron. Where does the energy come from? Because the atom absorbs 1 electron, it must emit a photon. It cannot absorb 2 electrons and emit a photon. It's not like this.
Oh, yeah.
So that it can absorb, for example, 50% of the electron, so that the electron slow down, not completely absorbed, or it was just completely slowed down by the atom, so that it emits the maximum energy. So the maximum energy should be the cutoff frequency, the minimum frequency. So otherwise, if we emit even lower, the energy is not conserved.
Okay.
Okay.
So if the energy is like below,
no, then you cannot have any photon emitted.
Because the atom is absorbing everything.
Yeah, the atom already absorbed everything.
Okay.
So and then it cannot get additional energy to emit even higher energy photon or even low frequency photon. It's impossible.
Okay.
So that the cutoff frequency is controlled by the energy of the emitted of the energy of the incident electron.
Okay.
Okay.
Good.
Good.
Yep. Thank you.
Yes. Yes. Oh, okay. Yes. Thank you. You also want? Oh, sorry. Okay. Good. Write down your name. Okay. Good. Good. And then you don't have to. So the other area about the assignment, okay, so for those of you who have not submitted the hard copy, remember submit the soft copy online by this Friday. Okay?
Tutorial there.
Sorry?
NTU learn the tutorial.
Yeah, then you learn the tutorial. Yes.
For this question, right, you can write instead of the operation, right? Let's try like that, like the explanation. After I do the calculation.
So this is for one of the question.
I just read it was.
I haven't seen this question.
The question 3.
这个教授。
I don't understand why. I don't understand like, why cannot use that one.
Oh yes, and then you just calculate what is the photon energy in the and then see whether it's exactly equal to the energy difference between the two.
Yeah, so I just related it as an explanation. Is it okay?
I thought it's true. But if you search.
Yeah, that's right. That's right.
Okay, then
This is okay. Yes. Oh yes, if you want to do now, it's okay. Okay, thank you.
Bro, so it's like that, right? So the photon is all the way from E1 to E3, right?
Yes.
So I test the three condition from E1
Yes.
to E3. Okay? So let's take the difference. So 13.6 minus this, we get 10.2. So this is for E2, right? Then this is 12.08, which is more than 11.294,
Yes.
right? So which means I cannot use this one. I need to use
No,
this.
no. If it's
that
more,
explanation?
if it's more,
Yeah.
it will not be absorbed. It must be exactly the same.
Must be exactly the same. So
Yeah,
if
it's
because it's 10.2, it's not exactly the same. Then I have a leftover of 1.09.
No, you cannot do this.
Oh.
You cannot left over. It either be completely absorbed. So what you should do, you should do here. Let me say, you cannot only get the E1 for E2. You should also get
E3.
delta E3.
Then I can issue though.
You get E3. So which means if it's not exactly this one, not exactly this one, it's something between. You cannot absorb.
Oh, it must be exactly the same. as this.
Exactly the same.
Oh.
This guy must be exactly the same. If it's not exactly the same, then you cannot absorb.
Oh, okay.
Okay, so which means if you are between this, which means the other E4 and E1 will be even larger.
Yeah.
E5 and B even larger, which means you cannot be exactly the same as any delta E.
Oh, so that means.
Yes, if you cannot, so which means only discretized frequency can be absorbed. It must exactly match either delta 2.1, 3.1, 4.1, or 5.1, and then it will be absorbed. Let the photon, the electron, to jump from one energy to the other.
Oh.
So if it's in between, and then it cannot absorb.
So it cannot, if it's lower, also cannot absorb. Higher also cannot absorb.
Higher cannot. It must be exactly the same.
That means my explanation can be there will be no state that I can absorb because you improve this already.
Yes,
Oh.
because because you say, okay, it's delta E1 is delta E2 is this, so which means both of them are not equal to my photon. So which means no other delta E can equal to my photon's energy, so that photon cannot be absorbed.
Oh, okay, thank you.
Okay.
Just now for physics, right, you mentioned there's three major parts.
Yes.
The cutoff frequency, K,
K alpha, K beta, and also the broad boundary response.
What is it?
The broad boundary response, which means the electron interact with the atom. So it's not to remove the electron from the atom. It's just the, for example, the atom has the nuclei, okay, so it transmits from this atom, but does not interact with the electron of the atom. But because the atom has positive nuclei, it will slow down the electron by Coulomb repulsion rates. So it slows down the electron and the energy has to be conserved. That energy will be transmitted.
So this is about conservation.
Yeah. The conservation of energy. When the atom is slowed down, it will transmit its kinetic energy to photon. That is the broad boundary response.
Oh, okay. Then the laser part, you see there's three.
Yeah, there's three.
So the positive feedback, is it the last part?
Yeah, the positive feedback is the last part, okay?
Oh,
Must be confined, not enough to stimulate.
State, then the
Population inversion.
Then
Population inversion, which means gain larger than loss. You can say this as either gain larger than loss or population inversion. Gain larger than loss. That is population inversion.
Oh.
So you can say, okay, either I need gain larger than loss, that is okay, or I need to achieve population inversion is also okay. So that's the last part I just gave you. Because this is what I directly copy from your lecture notes, so that will be for you, don't make your life too difficult. But I think this is too complicated. But what we want is a cavity to provide positive feedback. This is what I learned. This is when I was undergraduate. I think this is the most technical term. But I think this one is easier for you to understand, although it's very long. Cavity to provide positive feedback is I need the emitted photon to be confined in the system. The system is a cavity, okay? Long enough to stimulate the further emission. Long enough to stimulate the further emission just means, positive feedback. So, but anyway, you can either remember this, but as I said, this last one is what I mean by positive feedback. Atom confined in a system, so which means it's a cavity. Long enough to stimulate further emission from other feedback is a positive feedback. So normally I mark as I say, so of course when you say this is also okay, but I just mark from keywords I say. You mentioned metal stable state, mentioned population inversion or gain larger than loss, mentioned positive feedback, then I will put 4 marks.
So if it's in exam, then if you write this positive feedback, will it be accepted instead? Or does it be very specific?
No, in this case, as I said, you say I need a cavity for positive feedback. That's also okay. 4 marks.
Oh.
Okay.
So must mention in cavity.
You do all confine the system to stimulate further emission or to provide. That is also okay. Confine the system. How light can be confined if you did a cavity? No cavity, light cannot be confined. So confine the system, which means a cavity. Okay, so we are not that stringent. Okay, if you the meaning is you know more or less a simple will give 4 marks. Okay.
Thank you.
No problem.
I just write this way, all the marks. Just say no, the photon cannot be absorbed because the energy is not exactly the same as the energy needed to change the state. Just like that can already.
Yeah.
Okay.
Okay.
So we got any tips to how to study for the exam?
Start the exam. As I said, first go to the tutorial.
So I go through all the tutorials, right?
You go to all the tutorial, especially pay special attention on my summary, on my summary slides, and also go through all the tutorial class. I think this is the most important things. And then I think the summary lecture is more or less for the quiz. So you first go through all the tutorial, especially on my summary important concept. Use the lecture, LAMS lecture, to understand the concept and the question in the tutorial. So that is how you should prepare the final examination. I think that's a tutorial material is the most important one.
So this tutorial is the most important, really.
Yeah, because we have many examples.
Exam papers.
Yeah, after you do that, you try to do some elimination methods. I will also talk some questions from passive elimination methods next week.
Oh, okay. Then for the quantum physics, right? Because there's like 10 topics. There's like so
11.
11. There's so many topics. Then I must learn everything. So is there anything I can focus on?
So as I said, not everything in each chapter. So let me put it this way: all the 11 chapters will be tested, but not all the things in the 11 chapter will be tested. So you still focus on my summary. So for quantum equation, each chapter I only have 2 or 3 slides, so it will be defined. So the other thing I have not talked about, which you will be also tested. But all the 11 chapters has a chance to be tested.
Oh, okay.
So for quantum, I should focus more on exam paper questions.
For quantum, let me say I will highlight next week. For quantum physics, I think 3 important concepts is very important.
What's the
3. So first is of course the most important is this hydrogen atom. Yeah. So is the how the photon and hydrogen atom so something like that. So that way.
Okay.
So the second important concept is photoelectric effect.
The Einstein one, is it?
Sorry.
The Einstein.
The Einstein one, photoelectric also tested very often. So and then followed by today's the Schrödinger equation, wave function of Schrödinger equation. So that are the most important 3 concepts. So that is the whole assignment, if the whole assignment has hydrogen atom, right? Has this photoelectric effect, and also So the Schrödinger equation, because it's a last chapter, so that is it's the most important of this class. But maybe this 3 it will account for, so the probability of these 3 concepts to be tested is about 80%.
80%?
Yeah, 80% normally about this. The other 20, but as I said, I didn't mention say the other will not be tested, but it's the least important. For example, the photoelectric, the black body radiation, and also you can say, today I give you 2 questions about the X-ray generation. That is also, both of them are passive examination papers. Both of them passive examination papers, which means the X-ray generation and also black body radiation may also be tested, but may not be that important.
Okay.
But as I said,
chance of it coming out.
Sorry?
Lower chance of it coming out.
Yeah, lower chance for it to come out. And also, so I would say the most important thing is the hydrogen atom photoelectric effect and the Schrödinger equation. Then followed by the hydrogen atom, followed by the complex scattering. There is X-ray generation and the black body radiation.
Okay.
So the other part of it is
Scattering is the compound effect.
Yes, scattering is the quantum, is the complex scattering. Yes.
Okay.
Okay.
Summary is very important.
Yeah, of course, the summary is important. You just go to look at the summary.
For optics, usually